Our next lesson is on differentiability. We will look at how f prime of a might fail to exist, how differentiability implies local linearity, derivatives on a calculator, differentiability implying continuity, and the intermediate value theorem for derivatives. A function will not have a derivative at a point a f of a where the slopes of the secant lines for f of x minus f of a over x minus a fail to approach a limit as x approaches a. The next figure will illustrate 4 different instances where this occurs. For example, a function whose graph is otherwise smooth will fail to have a derivative at a point where the graph has the following. First, a corner, where the one-sided derivatives differ. Remember when we looked at the absolute value function and defined it as a piecewise function? The first half of the function is x, the other half of the function is defined as f of x equals negative x. Remember that the slope of one side of the function was negative 1. The slope on the other side of the function was positive 1. And the one-sided derivatives then would differ. Therefore, a corner is what we call it for an absolute value function where the one-sided derivatives are going to differ. Second, a cusp, where the slopes of the secant lines approach infinity from one side and approach negative infinity from the other. Sometimes we call this extreme case of a corner, or an extreme corner. An example is f of x equals x to the 2/3 power. Our third place where f prime of a might fail to exist is a vertical tangent, where the slopes of the secant lines approach either infinity or negative infinity from both sides. Our example is f of x equals the cube root of x. The other way I look at this is when you see a line that goes vertically, which is what a vertical tangent means. We know that a vertical line, by definition, is undefined. So where you have a vertical tangent, or where the slopes of the secant lines approach infinity or negative infinity, is where you're going to have the derivative fail to exist. Fourth, a discontinuity, which will cause one or both of the one-sided derivatives to be non-existent. This one's probably the most clear type of place where a derivative is going to fail to exist, where you have a type of discontinuity, which we've already talked about the different types of discontinuities, such as point discontinuity, jump discontinuity, and infinite discontinuity. Example, find where the function is differentiable. So let's find out where the function does not. We'll start with the easier one, which is the absolute value function. If we can figure out where the corner is on x minus 3 plus 1, think about how this graph is moved. This graph would be shifted 3 units to the right and 1 unit up. So where our new vertexes, which will be at 3, 1, or at x equals 3, is where the function does not have a derivative. So we can say it's differentiable, or it does have a derivative, everywhere except at x equals 3. On the next example, we will have to factor the denominator. Our denominator factors into minus 5 plus 1. Now, to determine if it's differentiable, we have to figure out if there is an asymptote line or a hole in the graph. So we need to figure out if x plus 1 or x minus 5 is a common factor of x cubed minus 8. So let's figure that out. I'm going to use the synthetic division to figure that out. So x minus the root would be 5. We use our coefficients, 1, 0 for the x squared, 0 for the x, negative 8. Bring down the first number, multiply and add, multiply and add. We can see before we finish it, we're not going to get an answer of 0. So let's go ahead and see if we can figure out if negative 1 is a root down here at the bottom. Again, bring down the first number, multiply and add, multiply and add, multiply and add. It appears that neither of these are a common factor of the numerator. Therefore, we know we don't have a point discontinuity, but we do have two vertical asymptote lines. So what this is going to tell us is that at x equals 5 and x equals negative 1, the function is not differentiable. So we're going to have every place except again at those points where it's differentiable. Remember to read what the question is asking for. Here's another example. Show the function is not differentiable at x equals 0. The function is defined as x cubed when x is less than or equal to 0 and 4x when x is greater than 0. The right-hand derivative we know is going to be 4. The left-hand derivative we know is going to be 0. Since the left and the right-hand derivatives are not equal, the function is not differentiable at x equals 0. A good way to think about differentiable functions is to look at their what's called local linearity. That is, a function that is differentiable at a point A resembles its own tangent line very close to A. So in graphing calculators, when you put in a function, if it's differentiable at a point, it will straighten out when we keep zooming in. You do zoom in, zoom in, zoom in at the point of differentiability. So that's if it's differentiable, it will straighten out to look like its tangent line. If it's not differentiable, it'll stay looking like a corner or a cusp. Here are some examples that you could put in your graphing calculator to check for the local linearity to see if it's differentiable. Here's an example of how this might look on a graphing calculator. Many graphing calculators can approximate derivatives numerically with good accuracy at most points of their domains. So this is what we call a numerical derivative, or in most graphing calculators it's known as nderiv or NDER. Most of the graphing calculators now are going to probably use the dy dx or the ddx notation to figure out the numerical derivative. So in the graphing calculator, instead of using the parentheses, you'll probably have something where you have a ddx, and then you'll put in the function, and it might ask you a ddx or f prime perhaps, and it then will ask you at what point, and so we put at x equals 2, and it will tell us what the answer is to the numerical slope or derivative at that point. This only works if you actually know the function. If you're given a graph of the function, it won't work. If you're not sure what point you're going to look at, it won't work as well. It's only to find a numerical derivative at a specific point. So take a look at your graphing calculator and see what notation you have on your graphing calculator depending on how old or new it is. Differentiability implies continuity. If f has a derivative at a, then we say f is continuous at x equals a. The converse then of theorem 1 is false. A continuous function might have a corner, a cusp, or a vertical tangent line and not be differentiable at a given point. Not every function can be a derivative. If a and b are any two points in an interval on which f is differentiable, then f prime takes on every value between f prime of a and f prime of b. We call this the intermediate value theorem for derivatives. Here's an example of some functions that we've been working with already in class, and we can show that the function is not differentiable at point P by comparing the right and left hand derivatives. So if we recall, the derivative of x squared is 2x. At 0, the slope, or derivative, is 0. Recall that this is a straight line, so its derivative is always going to be a constant, which is the slope, 1. So the limit, we'll say, as x approaches 0 from the left was equal to 0. And the limit, as x approaches 0 from the right, is 1. We're now showing that it's not differentiable because the left and right hand derivatives are not equal. Here's using some other notation in what I just explained. By using the definition of derivative, we can also arrive at the same answer. Sometimes they use a, sometimes they use b, and sometimes we can just simply find the derivative by keeping x in the function's formula and then finding the derivative, plugging in the number to get the value. This is assuming that we're going to plug in the point right away into the function. If you use the definition of derivative at a point, definition. And that's our lesson for today.